Okay, so sorry, some technical difficulties here. Okay, so last time we started talking about EM. It's not too loud? Okay. Which is really part of thinking about semi-supervised or unsupervised learning. So I want to remind you the context in which we talked about this and continue from there. So we talked about, as an example, on naive-based algorithm, right? So in naive-based algorithm, here is a classification problem, two values, n and v. And we realized that what we're going to do is we're going to just take statistics over the examples that were given to us, 10 examples, and then given a new example, we know what we need to compare. We actually did the math, and we know that for the example 1000, given the model that we learned, the parameters of which are here, we can actually make a prediction. And then the question that I asked was, let's assume I give you a lot of unlabeled data. And the question is what to do. I mean, we want to be able to use it. Clearly, there's information there. The question is, what should we do? And after some discussion and trying to convince you to give an opinion, we converge into basically two options. In fact, I'm going to get to them here. One is to choose examples, label them using the existing model that we have, and then use them. Maybe not use all of them, maybe use some threshold and just use the most confident one. But basically, label examples. That's option one. Option two, don't really label, but kind of keep a fractional label. Every example could be a V example with some probability and an N example with another probability. And we agree that we can actually take a data set with fractional labels and run naive Bayes, exactly the same way as we run it where the labels are 0, 1. Everyone agrees with that? So these are the two options, and really these are the basis for what we are going to do today. So the EM algorithm that we're going to run is based on this. And keep this in mind because you're going to see it as we develop the EM algorithm. And this is a version of EM that some of you who've used EM might have heard about. It's called truncated EM, where rather than keeping the probability distribution over the example, I'm actually committing. In many applications, actually, people prefer to use these versions, and there's a lot of literature on when and why, which I will not talk about. So that's what we want to keep in mind. And specifically, we asked the question at the end, what happens if instead of starting with 10 labeled examples, I'm going to start with 0 labeled examples? So I don't have this ability to learn an initial model and then continue with it. What are we going to do? And in fact, what we're going to do is we're going to continue with it, just like we continued with the existing model based on the 10 examples. The only difference is that our initial point is going to be weaker. We're going to guess. Or maybe if you have some idea of how to guess in a good way, you can incorporate it. So what we want to do now is to develop an algorithm that is based on this. And in fact, it's not only be an algorithm, it's a family of algorithms. Because as you will see, the algorithm is a framework, and we're going to plug in specific assumptions on the probability distribution. And given that, we're going to get a concrete algorithm, a concrete way to update parameters, to learn parameters. Okay, so then we started talking about some coin problems. And this is basically where we finish. One scenario is a very simple scenario. We have a coin. We toss the coin several times, not 6, I guess. And the question is, which coin is more likely to produce the sequence? There were 3 coins, and the answer that I wanted you to give, it took a long time, was what? Coin 0, yeah? The one that gives? But in this case, we actually don't know that yet, right? So I told you there are 3 options. There is alpha, there is P, and there is Q. And to figure out which one generated this, you want to know which of alpha, P, or Q is closer to 3/4. The second scenario is, first I'm tossing coin 0. If it's head, I'm tossing coin 1. Otherwise, I'm tossing coin 2. Right? So coin 0 controls the mixture, and then I have 2 distributions, the coin 1 distribution and the coin 2 distribution. And so the data that was generated this way was written here, where the red is the coin 0 toss, and the blue is what I got when I tossed either coin 1 or coin 2. In this case, which coin did I toss? This is coin 1. This is coin 2. And therefore, because you know that, if I ask you the most likely value of P, Q, and alpha, you can do it. And then we get to the more interesting question, where the scenario is similar. It's a mixture scenario. I'm tossing coin 0, and as a function of what I get, I decide which distribution is going to control the next few tosses, whether it's going to be the 1 or the 2 distributions. But I don't tell you what controls the mixture. So I don't tell you what was the outcome of 0. So now you cannot do what you did before because you don't know. Here you knew that it came from coin 1. Here you don't know where this came from. You don't know whether it came from the same one or not, and so on. That's the problem we're after. We still want to estimate the most likely values for P, Q, and alpha. And the interesting thing about it, yes?
How are scenarios 1 and 3 different from an information point?
So here I give you a lot of data points, and you don't know where they're coming from. Here you know that they're coming from 1 of 3 points. So a different scenario, no?
Uncertainty with both.
You have uncertainty with both. But if I give you, in this case, you have 3 options, alpha, P, and Q. And I ask you which one produced it, you can tell me. Let's assume for a second that alpha is a half, P is 3/4, Q is a quarter. Or let's say a third and 2/3. Would be more interesting. Which one is more likely to produce this sequence?
Alpha.
Why?
Because it is the highest distribution of that.
Someone, another view on this? Let's take the numbers that I've given. A third for P, the probability of head is a third. The probability of head for a Q in the Q is 2/3, and alpha is a half. Which of these is more likely to produce this?
Q, the 2/3 one.
The suggestion here is Q, which is the 2/3 one. Why is this more likely?
Because that's the coin that's given the more has than tails, and that's what you're observing.
So another way of saying it, okay, so one way to say it, it's the closest to 3/4, which is the observed probability here. And you can also say, let's assume that it's Q, probability of head being 3/4. Let's compute the probability, the likelihood of this data, observing this data under the 3/4 assumptions. It's going to be 3/4, 3/4, 1/4, 3/4. If I compute it under the P assumption, it's going to be a much smaller number, 1/4, 1/4, 3/4, 1/4. If I compute it under the half assumption, again, a small number. So this data is most likely to be produced by the 3/4. So that's what I know, right? So I can solve this problem. Here, problem is much, much harder. How would I start? Right? So you give me data points. I don't know anything about P, Q, and alpha. I just know they exist. Right? There exists an alpha that decided which of the coins will produce this sequence, which will produce this sequence, and so on. I don't know what alpha is, and I don't know what was the value of tossing the alpha coin. And I also don't know P and Q. Okay? That's the problem we're after. So it's a different problem. Agreed? And the question is, how are we going to do it? So hopefully you see the similarity to the NV prediction problem. Right? So think about this as examples. The label that was the red thing here is missing now. Okay? Yes? Because I have a typo. That's an easy question to answer. Okay, so what do we know? What we know is that actually this problem is hard in the sense that there is no known analytical solution to this problem in the general setting. We don't know how to compute kind of a closed form computation of these three parameters, even though it seems such a simply stated problem at least. What we're going to give is we're going to give an iterative algorithm that provably converges to a local maximum of the likelihood function. Okay, so here is the intuition for the problem. So the intuition is exactly the same intuition that we had for the naive Bayes NV problem. We have to start somewhere. So if we knew which of the data points came from coin 1 and which from coin 2, there was no problem. Agreed? And I'm just reminding you why there is no problem, because we know how to estimate maximum likelihood estimation. And in your problem set, you'll see that this is not the only way. Right? So this is this very natural estimation that you all guessed was done under an assumption. If I change the assumption, the estimation is going to be different. But either way, we know how to do maximum likelihood estimation. So let's go back to it. So if we knew, everything is fine. Instead, what I'm going to do is I'm going to use an iterative approach. I'm going to guess the probability that a given data point came from 1 or from 2. So for each data point, I'm going to guess it came from this. Under this assumption, I can compute the most likely value of the parameter. Once I have parameters, I can compute the likelihood of the data, just like we did a few seconds ago. If I know it's a quarter, I know what's the likelihood of observing HHTH. So I'm going to compute the likelihood of the data given this model. And now I'm going to re-estimate the initial parameter again. And I'm going to keep on going this way. So this is really what we have. If you have labeled, you can compute model parameters. If you have model parameters, you can compute label. Right? I'm going to use this in order to compute the likelihood of the data. When I have the likelihood of the data, as we'll see, we can compute model parameters, which is equivalent to computing labels. And that's going to be the process that we're going to go with. Okay, so for a minute, I'm going to assume that we know the parameters. And now I want to estimate which coin it is, which is our problem 1. I'm just saying, again, in a more concrete way, what I said before. Once I have this, I can use this to label, or I can use this label estimation, which coin it is just estimating a label, to estimate the most likely parameters, and so on. Here's my notation that I'm going to assume n data points. Every time I'm going to have m tosses, and hi is going to be the number of heads. Okay, so what's the probability that the ith data point came from coin 1? Again, I'm assuming that I have parameters. This is eventually be called the expectation step, and this is where the EM algorithm takes its name. We're going to have an expectation step, and then we're going to have an M step, a maximization step. So how do I compute the probability that the ith data point came from coin 1? Simply this. So I'm denoting it as P1I, the probability that it's coin 1, given that I observe this data. Using Bayes' rule, the probability of this data given coin 1, P of coin 1 divided by P of di. And let's just write it down. So probability of coin 1 is alpha. Probability of the data given coin 1 is P to the H, 1 minus P to the M minus H. Okay? And then I'm dividing by the probability of the data, right? So essentially this is marginalization, total probability table, formula, whatever you want to call it. The case that it came from 1 plus the case that it came from 2, right? It came from one of these. So notice, this is, you can think about this as a label, but it's best to think about it as the fractional label that we had before, right? I don't really know what the label is, but I know what's the probability that it's 1. So now what I want to do is I'd like to compute the likelihood of the data. Once I know the likelihood of the data, just like we did before, we differentiate and find the best parameters. So how do I compute the likelihood of the data? So I want to maximize the log likelihood of the data on these n data points, so the sum of log P of D given the parameters. Now, I actually don't know how to compute it because I don't know why. I don't know the label. So what I'm going to do is I'm going to marginalize over the y. So I'm going to write it as, this is still the sum over the data, log, and I marginalize here. So I have two options for the y. The problem is that now this becomes analytically difficult because what I have here is I have sum inside the log. I don't know how to solve it, actually. We have to do something. What we're going to do, and I'm going to say it multiple ways, is I really going to think about this as a random variable, right? It's a function of y, it's a random variable. And instead of maximizing it, I'm going to compute the expectation of this under the posterior distribution, P of y given something, and I'm going to maximize this. So really, we think about it as a random variable, and instead of maximizing the log likelihood, we maximize the expectation. There's another way to justify it and say that, which I'm going to write here. Really what we're doing, this is kind of a more hand-wavy argument, convincing you that it's okay to maximize the expectation. Really what we're doing is the expectation is an upper bound to the real log likelihood, and we're going to maximize this upper bound. To see that it's an upper bound, we can basically write the following. So this is the log likelihood. And then, as I said, I'm looking at this and I'm marginalizing it. Oh, no, sorry. So here what I did is I just used product rule. So P of D and Y is P of Y given D and everything else times P of D given everything else. Now notice what I have here is I have a random variable, and this is a probability distribution. So essentially, this is the expectation relative to this probability distribution of this random variable. So I call it expectation relative to y, because this is P of y, of this. So far I've written the likelihood as an expectation. But still I have the expectation inside the log, which makes life difficult. I'm going to argue that the log of the expectation is always greater than the expectation of the log, which is called Jensen inequality. I'm going to show you a picture in a minute that will convince you. But basically, that means that I started with the log likelihood, and I bounded it by the expectation of this random variable. And this is what EM is going to deal with. And really, the justification is that we're maximizing this lower bound on the likelihood. OK, so with this as justification, that's what we want to do. So we're going to maximize the expectation of this random variable. I'm writing this again. And the expectation is basically sum over all data points, the value of the variable times the probability that this variable is going to be 1, plus the value of the variable times the probability that it's going to be 0. This is directly from the definition of expectation and from the linearity of expectation. Notice that I had expectation of sum, but I replaced it with sum of the expectation. OK, the definition of expectation, just to remind you, is the sum of the value times the probability it takes the value, plus the other value times the probability it takes the value. OK, so now let's write this down. So again, expectation of this variable, I'm writing it explicitly, as I said before. So it's P1i times the value, plus 1 minus py times the value. I'm plugging in these probabilities. It's alpha p to the h, 1 minus p to the m minus h, inside 1 minus alpha q to the h, 1 minus q to the m minus h. And that's the expression that we got. Now I'm taking the log. So when I'm taking the log of this, that's what I get. Here for the alpha case, and here for the 1 minus alpha case. That's it. So what did I do? I computed P1i. I have a number. And then I computed, using it, the likelihood of the data, or the expected likelihood of the data. And now I'm going to use this expected likelihood of the data to figure out, OK, so what are the values, the new values, that maximize this likelihood? How do I figure out what values maximize it? I'm going to differentiate relative to these parameters. When I differentiate relative to alpha, let's look at this again. I differentiate relative to alpha, these terms disappear. And from the second part, these terms disappear. So what I get is that relative to alpha, I have sum over all examples, P1i over alpha minus this over 1 minus alpha. If you solve this for alpha, you will get this. What's the interpretation of this? What is alpha now? So what was P1i? P1i was the probability that the ith data point was coin 1. Let's assume that all these probabilities are 0 and 1. OK? So some of them are 1 and some of them are 0. So what does this do?
All the examples that is point 1, which is equivalent.
So essentially, we are counting the number of coins that were 1, divide by n, and it makes sense that this is alpha, right? Alpha should be the fraction of 1 coins divided by all of them. Now, really what we're doing is we're not counting 1s and 0s, but we're counting fractional labels. just like we said at the beginning, it's okay that some of these numbers are 3/4 and 2/3 and 1/3 and so on. Who cares? I'm counting a fraction of each one example, and this gives me all the one examples that I want, and that's my alpha. So it makes sense that this would be alpha. Agreed? And the same thing, if I want to differentiate relative to P and then relative to Q, again, if I do it relative to P, this guy is going to disappear. I'm going to end up only with these two things. And if you do it, you're going to see, again, sum over all examples. P1I is going to stay outside, H over P minus M minus H over 1 minus P. If you isolate P, this is what you get. And again, you can think about this, and hopefully it would make sense to you, right? So this is really all the 1 points, right? The number of the 1 points. Think about it again as ones and zeros. It's clear that it's the number of 1 points. If it's fractional, it's the sum of fractions, but still is the number of 1 point. So you want this to be in the denominator, right? And what you have here is a weighted sum of the one, given that it's a 1 point, how many H's did you get? And you want to average this. So this, and you want this to be your P, right? And the same thing is going to happen with the Q. So hopefully makes sense. So what have we done? We basically ran naive Bayes. It's no more than naive Bayes in a very simple case, right? Because all the tosses came from the same coin, right? So all I had to choose is whether it's 1 or 2, but within 1, all of them came from the same coin. And I call this the maximization step. This is the M. And we already did our sanity check here. So this is just a technical thing, which hopefully was clear, right? So at this point in time, when I'm differentiating relative to alpha, P, and Q, the previous estimations are constant, right? The P1I is a constant. Okay, so here is what we did, just going one step back. So we have two sets of variables, X and Y. Think about X as the data that we observe, Y as the label that you did not observe. And we have a joint probability distribution, P of X, Y. If we see everything, not a problem, right? So we always can maximize the likelihood, sum over all examples, log P of X, Y, given the parameters. What we have here is we have partially observed data. We don't see the Y. So if we want to maximize the likelihood of what you observe, we have to marginalize over what we do not observe. Instead of maximizing this, what we've done is really maximizing the expected value of this and did the argmax of the parameters. There are several other ways to explain this. We're going to go over more examples. I'm going to skip this detailed technical setting. I'm just going to show you one step here to refresh your memory. I did use the fact that the expectation of the log is less than the log of the expectation. And this is something that, you know, if you've seen convex functions before, you should know. So this function is a convex function. The reason it's a convex function is because if you take two values here and average them, so the expectation of the value of the function is larger than if you take the two x's, average them, and take the value of the function. Right? That's what it means to be convex. That the average of the y's is larger than the y of the average of the x's. Right? You see the blue line is above the function, the red one. That's the definition of convex, and basically Jensen inequality says that. In our case, it's a concave function. It's log, so it's just the other way around. So the line is going to be below the function. And therefore, the average of the function is below the function of the average. Okay? So I'm not going to go into these details. I'm going to, this is more advanced material, and I just want to summarize what we did. So it's really a very simple algorithm. Initially, we assume that we have some parameters. In the E step, we assume that we use the current guess, the parameters that we started with, or the current old parameters, to find the posterior distribution of the latent variable, the y's. Think about this as the label, right? The probability of z given the data and the parameters. This is the estimated variable. Once I have this, I can use this to compute the complete data log likelihood, or the expectation of the complete data log likelihood, which we've written this way. Right? It's the sum P of z times log P of x and z. Now that I can do this, I can differentiate this. This is my maximization step to get a new set of parameters. And I'm going to iterate this. So let's go back. Any questions on this? To the concrete thing. I see a lot of faces that I'm not sure. Okay, so here is the algorithm. Step one of the algorithm is this, E. Basically, I'm computing the fractional label, the probability that this data is coin 1. Once I have this, I skip the explanation and compute the likelihood of the data. I have P1. I have an assumption for PQ and alpha. I can compute this. This is my expression for the expected log likelihood of the data. And from this, I differentiate and get new values of alpha, P, and Q. 2 steps. Questions? Okay, so let's take another example. And the second example is going to be, again, I guess before second example, a summary. So, as I said, really it's a framework, right? A general procedure to learn in the presence of unobserved variable. It's a really important algorithm. A lot of the things that you're going to see today being done make use of EM, and the reason is that we want to be able to learn when some of the variables we care about are not observed. So it's a general framework for doing that. You'll see it in the called latent variable learning, or hidden variable learning, or just missing variables. So we did it in the case of a mixture of Bernoulli distributions, right? So we had the coin 0 that was the mixture controlling distribution. Really, it's important to realize that when people tell you in the literature, we ran EM, they didn't give you the algorithm, because they did not tell you which probability distribution they used when they ran EM. It's similar to tell you we ran naive Bayes. And hopefully you know today that telling you we use naive Bayes doesn't mean anything, because they still have to tell you which probability distribution govern the generation of the data to really understand how were the parameters computed. Same thing here. EM isn't well defined. We ran EM with this mixture of Bernoulli distributions, and every time someone tells you which family of algorithm. In practice, as I said, it's a very, very useful algorithm. When the assumptions are correct or pretty correct, it behaves beautifully. When the assumptions are not good, it doesn't behave well. And as I said, there are also variations, truncated and real EM, that sometimes you want to use one and sometimes you want to use the other. Okay. So before we did this mixture of Bernoulli, and I want to move to another example, which is going to be, again, something that some of you might have heard of K-means algorithm. Who has used K-means algorithm? Okay, so can anyone describe K-means to me? Yeah.
You switch up for clusters and you switch for K clusters.
Okay, so you have data. You want to split it into K clusters. You assume that K is given to you. How are you computing the clusters? So by clusters, I mean I want to split the group into K subgroups so that I know for each data item which of the K groups it belongs to. How do you compute it? Well, but mathematically, what would you do?
You compute the average of all the points belonging to the same group, and that's kind of like the average, and then you use that to recompute.
Okay, so let me repeat it. So you skip the first step. The first step that you had was, I'm assuming that I know for each point which cluster, which subgroup it comes from. Under this assumption, I'm computing the averages in each group. So I have the average of the first group, the average of the second, the average of the third, the average of the kth, and then?
I use all the averages to recompute the grouping result.
I regroup the points based on the averages. So how would I do it? Let's assume I have an average here. I look at all the points and think, okay, so now that there is an average here, which points actually deserve to be in the group of this average? And I have some metric. Let's say I take the closest to this point and put them in this group. And then, so I look at the K average that I have and split the data point between them so that something is being minimized, right? So for every data point, I place it in the group that belongs to its closest average. And then I have another grouping. Now I have another grouping. I compute averages again and split them. And I keep on going this way. So first of all, notice that it's an EM algorithm, right? But I'm going to give you a different EM algorithm, and we'll have to see what the differences are between this kind of commonly used EM, commonly used K-means, and the one that we're going to develop. But it's really very, very similar idea. So we're starting with a bunch of data points. I know I have to make an assumption. You didn't have to make an assumption, which, by the way, is okay because you just ran an algorithm. The algorithm, the way you run it, doesn't make any assumptions. In order to prove that the algorithm is correct under some conditions, this is where we have to make assumptions. So we're going to start with assumptions because we want to prove that this algorithm actually is doing something right, at least under these assumptions. So we are going to assume that the data is generated from K Gaussians. To make our life easier, I'm going to assume that the standard deviation is the same for all of them, but the means are different. So in this picture, you have two. So when I look at this data point, you don't know which Gaussian it came from. But each point came from one of these. OK, so and our goal is actually to decide for each point which Gaussian it came from, or we're going to do actually, or you can think about it as, rather than a disjoint clustering, I may want to just say, for each point, what's the probability it came from first Gaussian, what's the probability it came from second, up to K. Yeah?
What are the things that are being clustered together?
Points. In this case, points in the line. So I have a bunch of points. And at the end of the algorithm, I'm going to tell you this, and this came from this Gaussian, and the others came from the other. So at the end, I'm going to split the points into two groups in this picture, or two K groups in general. So again, just like we did in the case of the coin, let's make sure that we know what happens if there's no ambiguity at all. So if I knew that all the data points were taken from a Gaussian distribution with this mean, finding the most likely value of mu is easy. What is it? The average. Why is it the average? Right, so it is the average. All of you would guess that it is the average, and it turns out that we can actually, as you say, can prove it. It's a maximum likelihood thing. So in order to show it, this is the Gaussian distribution. And if I know that all of them came from this, right, so these are my m data points, I can write the log likelihood of the data. Okay, so I already took the log, so I have sum over all data points of this. I don't care about the constants here because I'm going to maximize it, but I care about sum of xi minus mu square. And if you think about maximizing this, which means you're going to differentiate this, and you're going to get, okay, the argmin of this, I'm going to call the best, the most likely mu. And if you do this, you're going to get that mu is the average. What? The average of the data point. So computing averages is the right thing to do. Okay, so now the real problem. The real problem is that you gave me a lot of data points and you don't know which coin or which Gaussian each one came from. And I want to split it this way. So as we said, what are we doing in EM? The first question we ask, what's the probability that this data point was sampled from the distribution mu j? Right? So we're trying to label. We make some guesses on parameters and we're trying to label the example. So this is my label, my fractional label. The probability that the ith data point came from the jth Gaussian is P of mu j given xi. Using Bayes' rule, P of xi given mu j, P of mu j divided by P of xi. And now I'm just writing this down. I'm assuming that the P of mu j's are uniform. I don't have any preference between the Gaussians or between which cluster I want to place the data in. Again, we could do it otherwise, but it's going to simplify our life. So I'm going to assume uniform. This is the 1 over k. And here I just wrote, again, P of x given mu divided by the probability of the data. Okay? Now I'm plugging in Gaussians, and that's what I get. So I have an expression as a function of my current assumption, which are the k mu's of what is the probability that this specific point came from 1, came from 2, and so on. Right? So what do I do now? So now I want to compute the likelihood. So I know that eventually I'm going to compute the expected likelihood, so I'm introducing the following notation. I'm going to invent this variable, the variable z's, k variables, one for each cluster, where zij is 1 when xi came from the j's distribution. Otherwise, zij is going to be 0. Notice that what we computed before is really P of zij, right? The probability the ith point came from the jth cluster. Because it's a 0, 1 variable, the probability of zij is the same as the expectation of the zij, and this is really what we want. So the expectation of zij is 1 times the probability that xi came from uj, plus 0 times the probability it wasn't sampled. Right? So this is, again, I'm reminding you the definition of expectation, and I'm going to use also the linearity of expectation, which is this one. Okay, so now with this notation, I'm going to write the log likelihood of the data. So what do I want? That's something that we know, right? The probability of y given the parameters is this. and I'm going to compute the likelihood given the observed data, or the log likelihood, or really the expected log likelihood. So the expectation of this, I'm going to push the expectation inside the sum, the linearity of expectation. So I have sum over all data points. These constants came also out. Sum over the jth, 1 to k, of the expectations of this times xi minus mu j. And now I have an expression for the likelihood of the data, just like we did in the coin case. Given that I have this, I can differentiate and figure out, notice that I know this, right? This is, I can differentiate and get the maximum likelihood of the mu j's. So I'm going to differentiate. Again, you can see what will happen when I differentiate. Really, I'm going to get the 2 outside, and I'm going to get a linear sum here. So I'm going to get this. Some constant. You know, I took the constant here and the 2 from here. They don't matter. Sum over all data points. The is x minus mu j. And if you isolate mu j from here, that's what you're going to get. And let's again see if it makes sense for us. So again, let's take the case where the is are 1 or 0 only. So either the point belongs to one of the j's or it doesn't. I'm not dealing with fractional. So then, what is the denominator here? It's the number of points in the jth thing. And what is this? This is the total number of points that I have. And in the numerator, I have all those points that belong to the jth thing. And that's actually what you want. And this is, by the way, the difference between, so what is the difference between the original algorithm that we described and this EM algorithm? This EM algorithm has 2 steps. The first step, where we computed Pij, the probability that the ith point belongs to the j, and what we had was for each I point we had k numbers, right? The probability that this point is in the first group, the second group, the third group, the kth group. K numbers. As a function of this, we now computed a new average for each one of the k clusters, right? K numbers like this. And now we can do the assignment again. The assignment is this. So think about this as the assignment of a points to a group, and this is computing the centroid of the group. Notice that here I have k numbers. In the original algorithm that you described, I had 1 number. For each point, I decided which cluster it belongs to. I put it in the clusters, computed the averages. Just like I do here, computed the averages. And once I have the averages, I did again the assignment, which means I decided for each point which centroid it belongs to, grouped them again, and continued. The only difference is that in EM, I do not commit each point to which Gaussian it came from or which group it belongs to, but rather I maintain a probability distribution for each data point on which of the k it could belong to. Questions? Clear? So really what you can see here is 2 EM algorithms. This is the EM algorithm, or the soft EM algorithm. The algorithm that we described before, where we actually make a commitment, is the truncated EM algorithm. essentially what will happen is you will look at these k numbers for each I, and you'll say, you know what, I'm choosing the maximum. Rather than maintaining the distribution, I'm going to take for each I the argmax over the jth. Right? The best cluster that this point wants. And you're going to do it for each one of the data points, and then you'll get hard clustering of the points. And you continue in the same way. So this sometimes is called hard EM, sometimes truncated EM. And again, quite popular algorithm that you will typically use if you have a good way to initialize your parameters. If you start with OK muse, in this case. In this case, it's going to converge faster and it's going to do better. If you don't know how to start your parameter, how to initialize your parameters, you actually want to run the EM algorithm rather than the hard EM algorithm. Questions? Yeah.
So after enough iterations, would you reach a equilibrium?
Okay, very good. So the question is, in theory, this is going to converge to a local minimum. You'll have to decide on the stopping criteria, but in principle, it's going to converge. It's not going to converge to a global minimum, which means that in general, when you run these algorithms, you want to restart it multiple times. That's the theory. In practice, as we said, you can run the algorithm even if we don't know that the data was generated from Gaussians. And sometimes it's going to work better than others, depending on really how the data looks. In all cases, you will have to come up with stopping criteria. Right? So how do I decide when to stop? What would be a sensible stopping criteria here? Yeah. You can say not much change in the parameters. You look at the parameters and they don't change. You can think about the likelihood function itself, and you can say it doesn't change a lot for a few iterations. I'm going to stop. So in fact, we're going to mention this when we talk about k-means in the last lecture or two. From the clustering perspective, we're going to mention some criteria for this. But basically, these are the ideas. Yeah?
Are there concerns for overfitting different types of algorithms as opposed to the more supervised ones?
So what do you want to call overfitting here?
Well, maybe the values that you arrive at the parameters have some dependence on the data set.
But the setting here is a little bit different. In what way is it different here than in the standard learning setting that we had? Any suggestion? What was the setting that we looked at, say, 2 weeks ago? We try to approximate a hidden function. Yes?
So, in the previous setting, we were learning on a training set and wanted to apply it to a test set. Here, we want to work on the given data set itself and segregating it.
Right. So we were trying to approximate a hidden function given a fixed data set, training set that was given. But we did not care about the performance on this training set. We cared about performance on future, previously unobserved data. And then overfitting was a concern because we could fit to the training data, do well on it, and do poorly on new data. Here, you just give me one data, and my goal in this specific case is just to do something to the data. Right? So it's not that I'm learning a model that I'm going to use in the future, but rather I'm going to split the data here. The notion of overfitting still exists here. What could be the notion of overfitting here? I did make an assumption. Just like in learning, I made some assumptions before I started to learn. What was the assumption here? K. I assumed K. And who knows whether I can split the data well and get good likelihood function for K equal 3. Maybe K must be 17. On the other hand, I don't want too large a K because it's very easy to put each data point in its own group. Everyone is going to be happy. So there is an assumption here, and this notion of overfitting is very similar to what we had before, and we didn't talk about it. In principle, you either search over K, or you could incorporate K into your EM as one of your hidden variables. It's going to complicate your life a little bit, but conceptually you could do that. Typically, people don't. People just try Ks. But this is actually a very important issue. Other questions? Yeah.
So you can still learn from EM if you have the labels, right? You can apply something like this.
I don't need to use EM if I have labeled data, right?
But still it's useful if the data itself has some missing values.
It's okay. So two questions, if I understand what you ask. So one is, if I have labeled data, I can learn from labeled data. I don't need to use EM. I could use EM if I have a little bit of learning labeled data. The 10 examples that we started with last time, it will just give me a good initialization, and then I'm going to go with EM. That's one. Two, in this case, the way I presented it is as if the label was missing, right? But for the same price, if you think about it, one of the variables could be missing. Doesn't necessarily have to be the label, and you can write the same kind of things. If you need a variable and it's missing, you can use EM relative to this.
A missing variable means like that it appears in some examples and doesn't appear in the others?
Okay, so we have to define what it means. In this case, we never had it. So that's kind of conceptually the simplest case to deal with. You never observe this variable. If you sometimes observe this variable, you'll have to incorporate this. Typically, you will incorporate it as a way to initialize the model in a better way.
Like the 10 examples.
Yeah. Okay, but that actually brings me to the next example. Oh, okay, we have... So basically, this is what we showed, right? So in what sense we found the best k-means? We found the best k-means in the sense under the assumptions of Gaussian distribution, and it's the same as saying that it minimizes the sum of square distance from the means. Okay, summary before I move to the next example. So I think we already said everything here. We've shown how to use it, this algorithm, as a way to estimate the most likely density function for a mixture of probability distribution. Both examples that we had were a mixture. Mixture of Bernoullis or mixture of Gaussians. It's an iterative algorithm. We can show that it converges to a local maximum of the likelihood function. It depends on assuming a probability distribution or a family of probability distribution. It's very useful. And we gave, the last example was actually a very, very important clustering algorithm. Perhaps the most important clustering algorithm, k-means algorithm, as an example of EM. And we talked about two extremes, soft EM and hard EM. Okay, so I want to, again, link it to something that you've seen before using this question. So let's assume that the scenario that I'm giving you is the following scenario. I'm going to give you data. For some reason, I like it to be n+1 coordinates now, x0 up to xn. And your task is to predict the value of x0 given, in test, I'm going to give you assignments to n variables, x1 up to xn, predict x0. What would you do? What kind of problem is it? It's supervised learning. Why is it supervised learning?
Because we have labels and the test set, and we're given one. So we're given the plain set, we are asked to classify one.
Right, so what's the label? Here, in this example. x0 is the label, right? So you were not confused by the fact that I changed the name to x0 rather than to y or something like this. Okay, so it's just the standard supervised learning problem. And the only problem that you have when you think about how do I solve it is which algorithm to use, or which representation if you want. Do I model it with a linear function? Do I model it with a quadratic function? Do I model it with decision trees? But you know how to do it once you make this decision. Yeah? Yeah, I want you to predict x0 given the other n. Isn't that the same setting that you're doing every time in supervised learning? I'm going to give you examples. No, in the data it appears. It's the label. Okay, let's read this again. Training. I'm giving you a sample of data points with n plus 1 dimensions here. You think about these as x, the features, and this as the label. Now, in the test, I'm going to ask you to predict the value of x0 given an example that specifies x1 to xn.
Then you never know the value of x0.
In the test.
Then they are not labeled.
I'm not sure what's not clear here. So x0, in the data I gave you this. All n plus 1. Each example is n plus 1 numbers, including x0. So that's your training data. Only in the test, I'm giving you n. It's the same scenario as you identify. The same scenario. I only confused you a little bit for a reason and did not call it y. Okay? If you change x0 to y, everything is just before. Okay. So you suggested supervised learning. Now I'm going to think about it slightly differently. I'm going to say, you know what? Here is how really this data was generated. I assume that these n plus 1 dimensional vectors were generated in the following way. Someone assume a hidden variable, we call it z. It has k values. And it takes the values with probability alpha z. Okay, so probability alpha 1 it's 1, with probability alpha 2 is 2, probability alpha k it's k. Given that I've chosen the specific value for z, now I'm assigning, we choose values xi for each of the observable xi's, n plus 1 things, right? 0 up to n. And I'm doing this with probability piz. Okay, so given that I chose z being 7, I have n plus 1 pi's. P0, 7, P1, 7, up to Pn, 7. Okay? So I chose z, and then I chose the example. And then, once I did this process, I gave you the collection of these examples. Okay? Now, before I didn't tell you how I generated the data, and you didn't care how I generated the data. You just said, oh, supervised learning, I know how to deal with it. Now that I told you how I generated the data, does this change your mind? You have another way of dealing with it? Yeah?
Let's look at like whether there's more ones in the ones that
Why?
because the probability is the same for each.
No, it's not. PIZ are, for each value of z, these are n plus 1 different numbers.
Oh, okay. I thought it was the same.
No, it's even more general than the coin, right? So I choose z is 1. Because z is 1, I have here n plus 1 numbers, probabilities, P01, P11, P21, N1, and I'm sampling these from them. And now I'm sampling z again. Now I got z equals 7. And I'm generating an example using P07, P17, P27, up to Pn7. And then I sample z again. Z is my coin 0 from earlier in the talk, okay? So every example, I first flip the z. I got the value z. I'm looking at which set of probabilities are going to generate the example. And then I flip the z again, generate an example, and so on. So how would you do it now? I gave you a hint. I told you it's like the coins. So now you have another option at least. All right? So you gave me the option of I'm not seeing this top part of the slide, supervised learning, but I want also the option of I do see this top part of the slide. What's the algorithm that you could use now?
But you're approximating the variable z with k values, and then kind of like for each of the data point that has x0 being missing, you guess which cluster does that point belong to, and then fill that x0 with the most probable value. That kind of thing.
Okay, but you gave me a detailed algorithm. What's the name of this algorithm? EM, really. Because it's not going to be exactly k-means because the distribution here is not Gaussian. It's just Bernoulli, given the way I told you I'm generating it. But it's EM, right? So it's essentially the coin problem with a little bit more, it's actually a little bit harder than the coin problem. In the coin problem, when I got coin 0, I then generated 6 consecutive tosses from the same coin. Here, when I got z equal 7, I had n plus 1 numbers to decide on the example. So it's a little bit harder than the coin, but conceptually the same thing. So I could run EM here, right? And EM is going to give me what? If it converges nicely, I'm going to get the alphas. I'm going to assume k, right? It will give me the alphas, and it will give me the PIZs. There's a lot of numbers here, right? So it's k times n plus 1 numbers. Just here plus k here. K plus k times n plus 1. Everyone agrees about the model? And everyone agrees that I could run EM, just the same EM that I ran from the coin tosses? Which one is going to be better? So this is the picture of what I have. I have z's. Given a value of z, I'm generating the x's. The z is generated with these alpha z's probabilities, and the x's with probability PAZs. Okay, so really I have two options here. I'm going to call one parametric option. I'm going to estimate the model using EM. Why is it parametric? Because I need to assume a model, right? So I cannot do EM without an assumption, so I'm going to assume, say, Bernoulli on the PIs. Non-parametric is the original suggestion, learn x0 directly as a function of the other variables. Right? So basically disregard the top part of the previous slide. Think about it as a problem of the first part of the class. And the question is, which one is better? And it's a fair comparison, right? So you have a case, a scenario, where you can think about, I can do EM, I can learn another function, which one's going to be? So first of all, it has to be clear that once you have done EM, and you know the alphas and the p's, if I give you a data point, you should be able to compute the most likely x0 given x1 to xn. So if you're not convinced about it, good exercise. Convince yourself that you know how to compute p of x0 given all the xi's once I give you all the pi's and the alphas. That's part of the EM algorithm, really. If you go over the EM algorithm, you've done it. Now, it turns out, when you think about which one is better, that if k equal 2, it so happens that x0 is a linear function of the others. So it's now becoming a really fair comparison between linear learning algorithms and EM, assuming k equal 2. If k is not equal to, becoming harder, it's not a linear function. You can still learn it with a linear function and see what happens. The issue is that if k is unknown, if k is known, EM is going to perform well, whether it's 3 or 4 or 5. But if you don't know k, you assume that it's 5, but really it's 3, or vice versa, it's not going to perform so well. And then maybe a direct learning algorithm is going to beat it. So it's actually a very interesting scenario. And from my perspective, what I want you to understand is that you have a problem that you can think about from multiple perspectives. You can always think about it this way. Right? The data was generated somehow. And this is a sensible way to think about it. But you can also disregard this and say, oh, that's the data. So a good way to think about, in fact, you're going to develop this or some version of this in the next problem set. OK, so I'm actually not going to do this. Stop here. Final questions? OK, have a nice weekend.
Hi, Professor.
Hi.
I decided to drop this course and retake it next semester.